requires an awful lot of energy to melt. The temperature doesn't change. That energy is there. It's melting the ice. We have a job to do. All right, now as for wireless communication in particular, it all basically, for all intents and purposes, electronics started in 1914 with the invention of the vacuum tube. That was practical. And it went on, improved. We get these small radios. They're not giant room size anymore, but you put them in your trunk. Then you can carry them around as a very heavy purse, basically, and then things have been getting lighter and lighter since then. I personally got started in the wireless business technology in 1968 when we were working with vacuum tubes, then transistors, ICs of increasing complexity. Now, one of the things that scared the daylights out of me when I prepared this slide is the length of the green line compared to the length of the blue line. And that I have seen a lot of things because I've been a participant in this business for half of its existence. That will never be true for anybody else here. But I've witnessed a lot of things. And being a participant, I've seen a lot of the boxes that we've been building around ourselves that we have to somehow get a handle on. Now, those of us in the radio world know that there's a trade-off between efficiency of our circuitry and the linearity that the circuitry provides, and the accuracy of the signals that we get out of it. I said before the practical vacuum tube started in 1914. The date of this patent on how do we solve the efficiency problem in our radio systems is April 27, 1915. It was recognized really fast that we have a problem. And how many people in here are researching amplifiers now? Nobody. All right. We still have a problem. And after a century of experience, of practice, we still have a problem. So what's going on? Well, a little more history of mobile communications. That used to be this big box that's stuck in the trunk. We had a big cable that goes up to the battery, and another big cable that came to what looks like a telephone up by the driver, which we effectively called the snake. And inside this big radio box in the trunk was a whole bunch of vacuum tubes and things. These are pictures of boxes that I personally owned. And the nice thing was you could be anywhere in the city and make your phone call through one big antenna that was sitting in the middle. Not much changed between when this was done in the early 1960s for about 25 years until somebody decided that we could take this coverage of one city and break it up into a whole bunch of little pieces. In fact, we needed to if we're going to actually cover, get service to a lot of different people, because how many frequencies do we have? We're not changing that at all. So we have to reuse the frequencies. That brought on cellular systems. We got this type of technology going on. And the big deal here is there's a commercial merge of computer control with radio technology. Before then, they never talked to each other. Right? In 1978, when I was a senior at Berkeley, I would say that there's two types of circuits in the world. Those that work and those that are overdriven. And my digital colleagues would say, all right, smartass, we agree there's two types of circuits in the world, those that know what they're doing and those that can't make up their minds. Right? This gives you a feel for how much cooperation it was between the digital and the analog radio communities at that time. Things have now changed. And so now, what do we got? These things are everywhere. Everybody in this room is guilty. What does it take to make them work? Well, it takes these beautiful things, me, with all this radio antennas on them. However, most of society doesn't seem to agree with me on the beauty of that thing. So we have to spend a lot of time making them look like trees, palm trees. Here's one from Arizona, saguaro cactus. That, it looks about right from a distance, but inside that is a cell site. We have to hide them. People don't want to see them. nothing comes for free, right? We generally only see the mobile devices and maybe an access point or some of these cell sites if you know what you're looking at. But there's a lot of stuff going on behind the network, and we're going to make everything available on demand at any time. And all of it draws power. So here we start to get a feel for what does it take to make this stuff sustainable. So what does some of that background look like? Well, we've got the digital network core, and there's just a few digital circuits there. Baseband processing, switching data centers to actually connect with the overall network, and of course transmitters, receivers, and backhaul. Their relative contribution to the LTE network is shown here. So we've got about 20%, about a fifth of it in this digital stuff, 24% more in the switching piece, almost 60% in the radios. So clearly, if we're going to make a difference, we have to make a difference on the radios. But still, you've not got 60% down, you've got this 40% of the digital stuff. And so there's an awful lot of good things that have to happen there. And if you take a look at all the energy that's being drawn at the system, and there have been a lot of research people over the years that have looked at this, the communications infrastructure now power draw is above 3% worldwide, which means that it's on par with all the energy that's being used for all of aviation. So you look at this phone and everything that goes along with it. And think about all the 10,000 airplanes that we have lifted 7 miles into the air, and then accelerate them to 500 miles an hour, and then slow them back down again and bring them down gently. All these things, all the airports, everything. Right, now, the aviation business and that energy is holding pretty constant because things are getting a little more efficient as it grows rather slowly. However, when we talk about the communication network, we've got CAGR, compounding annual growth rate, is 47% right now. That means in 8 years, the thing grows by a factor of 20. So 20 times 3 is what? 60% of the electricity on this planet, just for this. Do you like your lights? We have a problem. Do we have enough electricity to run this network? No, we don't. There isn't enough electricity on planet Earth to run the communication network as it's currently progressing with the technologies that it's currently using. So, what are the goals? You look at the goals for 5G. You want 10,000 times more traffic, 100 times more devices, flat cost, flat energy. 10,000 times 3 is how many percent? We have a problem. And when you have a problem, my first thing I do is go to the ultimate motivator, Albert Einstein, and lots of great stuff out of his mouth. But the important thing here, I want to cover that, never stop questioning. Curiosity has its own reason for existing. What questions should we ask in order to solve this problem? Why is the power draw what it is? Have we hit physical limits already? And if not, where can we get large improvements quickly? Right, because that's what we need. And so let's, a little bit of history. As there's history, we've gotten our 2Gs, 2.5G, 3G, LTE, 4G, 5G, and all of these signals have particular property that's called the peak average power ratio. How much envelope variation does the modulation have? And you overlap that on fundamental circuit theory for linear amplifiers. And a Class A amplifier at best is 50% efficient. You'll never ever get there for lots of reasons we can talk about. But assuming that we do have ideality, as the peak average power ratio is increasing, the peaks still have to stay in the linear range of the amplifier, so you're spending more and more time in the middle where your power dissipation is going up, your efficiency is going down, and that limit curve is right here. So as the peak average power ratio is going to 6 dB, you're never going to be above 23%. At 10 dB, you're never going to be above 17%. So we're baking into this, by the signal design that's going on, if we're going to use linear circuitry, a limit on the efficiency. Why does that matter? That matters because let's say I have a 10% efficient circuit. That means that 1/10 of the power that goes into it is coming out. I need a power supply that's 10 times too big, of which 9 of that is going to go straight to the heatsink. So economically, I have at 10% efficiency, power supply is 10 times too big. Heatsink that's 9 times is absorbing 9 of those 10 units, and I'm only using this one. That's not cheap. You're paying for the electricity, you're paying for the power supply, which is copper and iron, which is not light. Then you're paying for the heatsink, which is aluminum, which is also not light. And so you end up with people who are building these small cell prototypes now that are being used for trials, and they work perfectly well for trials, except that they weigh 100 pounds. You need a crane to install these things. And that will not happen to make this stuff go to scale. And so we need to ask more questions, and we need some new traditions in how we approach the problem. Right? Following the rules that we have is not going to work. So one possible thing is, well, every amplifier that we've ever built has an input port, an output port, and a power supply. But that power supply is actually another input. So let's call it a port, and then what can we do with it? And what ends up happening is the efficiency, this efficiency curve doesn't hold for this case. And there are things that we can do to bring the circuit efficiency very far up. But we also have to recognize, what is the problem we really have to solve? And the problem we have to solve and make this stuff work is that that output waveform that's coming from the transmitter going into the network that we're going to use has to be correct. That's all the standards say. You're going to have your distortions below these certain levels. It doesn't say anything about how. So that frees us as engineers to think about what the physics is. What does physics allow? What paths does physics provide us to get a precise waveform? And I count two. One is linear network theory. That's what we're used to. We use a DAC and generate very accurate signal, and then use linear amplifiers to make it bigger. But there's another one that's about a century younger from Nyquist, which is sampling theory. Nyquist gave us a set of rules. It says if you do all these things exactly right, you will at the end have exactly an error-free waveform. Okay, however, the circuits that go along with both of these are very different, and the math that describes it is also very different. And so we can imply that maybe we're going to get different performance out of all of these. So, what is it we're now next really trying to do ourselves for a system? Well, we use linear transmitters, which means we have this linear load line overlaid on the transistor, and we need to move along that load line in a proportional linear fashion in order to get accuracy of the output waveform. To the extent that that doesn't happen, we have linearizers to fix it. But if we want an efficient transmitter, you've got to stay away from these high power dissipation curves, because this is P equals IV. Right? Each one of these is constant dissipated power. And we really want to have low power dissipation, and so an efficient transmitter follows this kind of curve, not this one. Therefore, we conclude that a linear amplifier can never be efficient. This trade-off we've had from the very beginning is a direct consequence of Ohm's law. How negotiable is Ohm's law? I've tried, doesn't work. Right? We have to find, if we're going to be efficient, we have to find something that's not linear, but still very precise. Or if we stay with linear circuitry, we have to understand it's going to cost us. Right? Just the way it is. So, what what we want to do. We want to take something that's changing from this at scale power flow of 11% efficiency, where this is what we want out. What goes in DC-wise is 9 times more in this case. We have input power that just gets dumped into the heatsink. So this whole idea of power added efficiency is meaningless. It's not what happens in the world. And then everything that's left over gets dissipated. And we have to pay for the power supply, we have to pay for the power going in, and we have to pay to take the power to heat away. Very expensive. What we really would like is we want our output power to take pretty much just the power that we need, get to that kind of efficiency. And by shifting from linear systems to the sampling theory, things do improve quite a bit. So this is just one aspect of the problem, right? How do we use less energy to make the same signal? What we really need to do is go after more global optimization. However, that means changing the modulations. They do exist, they're not in the standards, and so we have to change the standards if we're going to actually take advantage of that dimension. That, as Dr. Lin would say, is a decade-long process, if not more. So that's not going to happen quickly. So we have to pay a little more attention. But if we do, we can apply to lower frequencies anyway with sampling techniques to existing signals and get them to work really well. And so for those of you who are students, I don't care if you're a radio person, analog, digital, digital processing, all of these are vital in order to make this thing work. And I look forward to talking to you later. Thank you.
Any questions from the audience? Any questions?
So digital pre-distortion has been around for many years,
Yeah.
and I have fought and fought, it seems like, with amplifier providers to implement nonlinear amplifiers and digital pre-distortion to get the power consumption down. Why do you think it's so hard? Why do you think?
Because with a digital pre-distorter, if you're trying to make things linear, right? You're trying to force things to be very linear on this, and to take advantage of this little corner up here, right? Because this is where most of the distortion is happening. And of course, if your input goes into the cutoff region, that's a very nonlinear effect as well. And somehow you still need the output signal to exist, even though there's nothing going in, right, to the output network from the transistor. And so what the DPDs are doing, they're trying to tolerate an amplifier spending more time down here, more time up here, and less time up here. But the DPD also takes power, and you have to include the total power of the whole thing, because that's what's going to get installed in the radio.
But I mean, I've seen it. There's companies that work that have done it, and it's still a pretty big.
It works.
Maybe it's not a problem. Maybe it's not much of a solution as this one.
Don't get to the performance you can get from here.
Are there solutions available that are doing this now? Or you guys have amplifiers for various?
No amplifier. No, the whole point is, and I need to get out of the way. This is an amplifier. This is not.
Okay.
All right. This is make it at full power. It's an at power sampler. There's no amplifier at all. Okay. Yeah, it's a completely different way of doing things. Even though the circuitry looks almost identical, how it behaves is completely opposite.
And those solutions available today?
There are very few companies that are working on this, but yeah.
That's the keep the discussion offline.
Yeah.
The speaker will be here. So let's thank the speaker again. Our last speaker is So our next, last speaker is Cameron. He's also a PhD student here at Davis. He's going to talk about this deep bandwidth aware technology. Let's welcome the speaker.
Hi everyone. Thank you. My name I'll go through very quick because we are limited with time. I'll be talking about how to do deep learning when there's a band limitation. Right, so this is the agenda for today's work. And let me talk about cloud AI applications. So source nodes, like smartphones, they have less memory and less computational power. So they often use remote servers or cloud to do their deep learning tasks for them. So for example, a source node like this would take an image of a dog and send it to the server to classify it as husky. Most of the time, the channel which we send this information over is band limited. So that means simply you cannot send as much as data you like over the channel with low latency. Because of that, images or videos are encoded to reduce the bandwidth usage using codecs like JPEG and JPEG 2000. But the original design objective of these codecs is to reconstruct better quality images on the server for visual perception. And they are not necessarily optimized for deep learning tasks like this. So in this talk, I'll be looking at how to optimize existing codecs for deep learning tasks. And I'll be focusing on JPEG 2000 codec, which is like the recent popular standard for image compression. And it has several blocks, and it takes RGB image as the input, and it then centers the image. Then there's a conversion from RGB domain to YCBCI, which is another color domain. Then the important block, DWT, which is discrete wavelet transformation, which transforms spatial domain to spectral domain to facilitate compression. Then this is where we lose information. If we have a bandwidth limitation, we quantize our coefficient values before encoding and generating the stream, and this is what we send over the channel. And if we look at what DWT does is this. If this is our input, which is RGB, it has 3 channels, right? If we do DWT, which is transformation, it produces again 3 channels, 1 for each channel. And if you look at one channel, it has 4 subbands like this. 1 low frequency subband and 3 higher frequency subbands. And a lower frequency, of course, is an approximation for the image, and higher frequency are, they contain different information. And for deep learning tasks, to make use of this, we can arrange these 12 channels this way to have the input, and now the dimension is half of the original input. Okay. So let's talk more about quantization, how we lose information. According to JPEG 2000 encoder, you have your input X with floating point precision, which takes so much bandwidth. So you divide by a step size called ds, then you round off the value to the nearest lower integer and get qx, which is an integer. So these only consume less bandwidth to transmit compared to the floating point precision numbers. But then again, this division by the step size can be represented as a parameter ws, which has the range from 0 to 1, which I'll be using later. So if you look at the step size, and JPEG 2000 has different values for these step sizes based on what subband you are on. That means, for example, this lower frequency subband uses smaller step sizes. That means when you lose information, you lose less information from these subbands and more information from these higher frequency subbands. Now, to see what is the effect of this quantization process, this is the experiment we can do. So we can increase the compression ratio by increasing ds value, which is the step size, and each time I'll be reconstructing the RGB image and the DWT coefficients corresponding to that. Then we can use, for example, here we are focusing on classification. So we can encode images like this, get these inputs, and feed it to a classifier, a deep learning classifier to classify images. So x-axis here is the bandwidth, the allowed bandwidth, and y-axis is the accuracy. As you can see, if we have less bandwidth, our accuracy drops drastically because of the limitation. So with this, we formulated the problem. Now, we have seen that the classification accuracy critically depends on the allocated bandwidth, and these codecs like JPEG 2000 have predefined quantization step sizes. That means they have a predefined optimal table for the step sizes. But even these are not optimal for deep learning tasks like classification or segmentation. Can we do better? So for that, to address this issue, we propose a joint compression and learning network that has the awareness of bandwidth and the task that we want to learn. And we saw that we have 12 bands, 12 sub-bands. That means we have 12 congestion step sizes to optimize, right? So we are supposing one net for that. It has two blocks. One block that quantizes, that learns how to quantize, and a deep neural network to do your task. In this one, we assume it to be classification. So it takes unquantized DWT coefficients, which can be extracted from the encoder. Then it quantizes. Then this deep CNN can be a classifier, and it classifies labels according to that. Then, okay, I'll skip this. This how to implement the fun block, which is so easy, and it only takes 12 parameters. We have 12 bands, and it follows by a differentiable flow function that we have an approximation to make sure this whole network is backpropagable and is learnable. And so the loss function of the network has two main functions. The first one is a classification loss, which says how well we classify or how well we do the task. And we have a point loss function to say how much bandwidth each image consumes. We want to minimize both of them. And we can change the lambda value to emphasize like I want this much bandwidth. Then we can implement the L1 using like L2 regularizer, and during training what we want to find out is the optimal W parameter, which has 12, a vector of 12 parameters for a given bandwidth value implied by the lambda value. And these are the results. So the results are on Cypher 10, which is a classification dataset which has 10 classes. And we experiment on two DWT wavelets. As you can see, so x-axis is the bandwidth, y-axis is again the test accuracy. The blue curves are the ones that you get if you use conventional codecs like JPEG 2000. And so the classification accuracy degrades, and the red curves are the ones that uses the learned quantization intervals from the suggested quantity. As you can see, the gradient of the curve is smaller compared to the baseline curve, which promises like better accuracy improvements for a given bandwidth and vice versa. For example, one use case, if you are interested in getting 88-pin accuracy for classification, you don't really have to transmit 0.6 kilobyte. You can just get the job done with 0.35 kilobyte, and vice versa. If you have a budget from somewhere here, bandwidth budget, you can get more accuracy with the red curve, with the learned approach. And it's really easy to apply for existing commercial codecs too. What we are proposing is this. So we propose the training to do on the server, on the cloud. It can be offline. Then we converge the network to learn W naught and theta naught. Right? Then after learning this W naught, we can hard code it on your smartphone to quantize accordingly. Then you can send this saved model or trained model to the server. So each time, if I have a bandwidth limitation, I will select the learned set of parameters. Then I have to notify the server to use the according model for that. With this, you just have to hard code the parameters for the codec to practice and apply. So as a conclusion, we propose a joint network that can do classification or learning and the compression with the awareness of the bandwidth and the task. And with that, we achieve significant accuracy improvements for a given bandwidth or vice versa. And the good thing with this is the fun block is simple to implement, and it can be applicable to any task. Like if you have classification, you have your classification network, you attach your fun block, learn the parameters, hard code it in your JPEG 2000 codec, you're done. And if you want to do segmentation, same thing, get your network, then learn the parameters, hard code it, you can get the accuracy improvement. Thank you. And I'm available at the post session too if you have questions.
We have time for one quick question, and Chairman will be in the poster session. If you have more questions, you can go to his poster. Any questions from the audience? One quick question is that it seems that right now smartphone is powerful enough to do this on the smartphone itself, right?
Yeah.
Why do we need to upload to the
So it's not exactly for smartphones like that. There are like low power nodes like cameras that you have memory limitation. You cannot, because the models for like classification accuracy can be like several parameters, a million parameters. If you don't have like memory.
I see. Okay, great. Let's then thank the speakers, all the speakers again. Thank you for attending this session.
Thanks for organizing.
Oh, I'm not organizing.